Hi everybody. Hi everybody. I'm Tony E at Show IP Interface Brief, and today is day 57 of 100 Days of Labbing. Tonight I'm going to do a little lab because last night I left off with something that was unsolved, and so tonight I set out to go ahead and solve it and understand this technology, and that technology is a Bgp Backdoor. First of all, it is just one simple little flag on the end of a network statement, and there's nothing more to it than that. But there is some underlying theory and some unexpected behavior, unexpected on my part, and that's based on my confusion from yesterday. So I set out today to actually get to the bottom of it, and that's where I'm at today. So actually I spun up a little lab. I'm going to do a little whiteboard session. I'm going to do a quick lab, and then I'm going to show, I think, exactly how it's supposed to work. And it's pretty cool. And I think after this, I'll go ahead and put it to rest and start on something new tomorrow. But I'm really happy I went through this because yesterday I thought that maybe I had a bug in my lab software, or that I just didn't understand it clearly, or that I was misconfiguring something. And today I went ahead and labbed this up with two variants of iOS images in EVE-NG. So I used the IOL platform and I used the viOS platform, both with the same results. So this was a pretty good experiment, and I'm really happy I followed through with it. So that's what I wanted to share tonight. I didn't want tonight just to be a short vlog. I actually wanted to share something, to document it, to make sure I understand it. You know, that's what they always say, right? In order to prove that you understand something, you should be able to explain it to someone else simply. So that's what we're going to try and do here tonight. Okay, so I'm going to start with a small whiteboard session and kind of draw out the topology we're going to work with, and we're going to kind of go through this sort of like using the scientific method, right? We're going to make a hypothesis, we're going to test our results, we're going to validate, and then we're going to take it from there. Okay. So what I have here is my whiteboard. How I set up this lab was just 3 routers. I call it like the string of pearls because it's just 3 routers all connected to each other. This is going to be in the lab that I'm going to show you guys. This is going to be a router 4, router 5, and router 6, and that's because I have routers 1, 2, and 3 also in the topology, but they're doing something else. They're not directly connected to what I'm showing you here. In between routers 4 and 5, we're going to run OSPF, and that's going to be area 0. Between 5 and 6, we're going to be BGP eBGP, and this is going to be autonomous system 65,000, and this is going to be 65,535. And what else? And on router 4, I went ahead and threw in 3 loopbacks. I went ahead and did loopback 1, loopback 2, and loopback 3. And loopback 1 is 1.1.1.1, loopback 2 is 2.2.2.2, and 3.3.3.3. And what I did was, it was how I included the loopbacks in OSPF. I thought, well, let me finish. Go ahead and explain that. So loopback number 3, I went ahead and included that in area 0. Excuse me, that was incorrect. On loopback 2, I included this on area 0. On loopback 3, I made it area 3. And on loopback number 1, I made this redistribution. I redistributed that as a connected route into OSPF. So what that's going to give me is, here on router 4 and on router 5, it's going to give me one OSPF E2 route, which is external type 2, which is going to be our 1.1.1.1. It's going to give us our intra area route, which is, let's see, it's going to be 2.2.2.2. And I'm going to get OSPF inter area, which is going to be 3.3.3.3 because it's coming from another area. So right now I have IP addresses configured between 4 and 5 and between 5 and 6, but I have not configured any protocols yet. So let's go ahead and configure the protocols, establish the loopbacks, make sure we have adjacencies, and then we'll take the next step by implementing BGP Backdoor, making our prediction. The networks we're going to use for this is going to be 10.1.12.1 and 2, and this is going to be 10.1.23.2 and 3. These are going to be /24. Okay, let me pull up the routers here. Okay, so what we're looking at here in the bottom left-hand corner is router 4, and that's our router that's all the way on the left side of the whiteboard. In the upper right is router number 5. That's our middle router. You can tell by the interfaces here, and actually looks like one of my interfaces is down. And then the bottom right is router 6, which was all the way on the right side of the diagram on the whiteboard. All right, let's make sure our interfaces are up. And over on router 4, show IP interface brief, just to make sure we're up. Let's make sure we have reachability. I'll do it from the middle router so I can check both directions. Let's do, we're going to ping the broadcast address, see what answers. And we can do show adjacency to see what's on the other end. So we can see, in this case, router 4, and we can see router 6. I guess we could have also have done show CDP neighbors, would have gotten us there as well. Okay, so on router 4, let's establish OSPF on our interface between router 4 and router 5. So interface gigabit 00 and do IP OSPF 1 area 0. We'll come over here to router 5. We're going to do the same thing. And we should see an adjacency come up. While that's coming up, we're going to create our loopback interfaces on router 4. So interface loopback 1, IP address, and we're just going to give it a 32-bit mask. Interface loopback 2. We'll call it 2.2.2.2. And again, a 32-bit mask. In interface loopback 3. So let's check our interfaces. They're up. Now let's activate OSPF on those interfaces. So we're going to put loopback number 2, which is on router 4 in area 0. So interface loopback 2, IP OSPF 1 area 0, and interface loopback 3, we're going to put that in area 3. So IP OSPF 1 area 3. Now we can check this by doing show IP OSPF interface brief, and we can see our interfaces that are participating in OSPF and what areas they're in. So if we go to our OSPF neighbor, we should now see these in the routing table. we see our loopback 2 is an intra-area route, and loopback number 3 is inter-area. We don't see loopback 1 yet because we did not redistribute it yet. So let's do route map, and I like to do OSPF redist match interface loopback 1. Then we'll get into OSPF. Redistribute connected, and we'll run that through a route map called OSPF redist. And that's going to do type 2 by default. So I'm just going to come over here to the adjacent router, show IP route, and there we see our external type 2 loopback. Okay, on router 5, we want router 5 and router 6 to be eBGP neighbors. So let's go ahead and configure that. So we're going to do router BGP 65,000. Let's do neighbor, and we're just going to use the directly connected interfaces. 65.5.35. And this one, router BGP 65.5.35. And this needs to be neighbor 10.1.23.2 and remote AS 65,000. We should see an adjacency come up, but we're not going to be exchanging any prefixes by default, at least not upon adjacency. And the idea here is I'm going to redistribute our learned OSPF routes, which are on router 5, into the BGP, or into the BGP table. And I expect those being router 5 and 6 being eBGP peers, router 5 to advertise those over to router 6. So router BGP 65,000, and let's do redistribute OSPF process ID 1, and then let's do internal routes. Oh, excuse me. Let's do match internal routes and external routes. So now on router 5, if I do show IP BGP, I see our BGP table is including our external loopback, both of our internal loopbacks, because they're intra and inter-area routes, so they're internal, as well as our connected interface, which is also participating in OSPF. So if we come over to router 6, it's sort of the end of the line for router 6, so do show IP BGP. It is only preferring one path, so we see the preferred caret there, and show IP route. We can see them in the routing table, learned via BGP. So yesterday, the trouble I was having was I wanted to apply the backdoor statement on router 5, the middle router, to some of these prefixes that I was redistributing from OSPF into BGP. And I noticed that when I did that, the prefixes disappeared. So what is supposed to happen is it's supposed to allow, let's say, when you're exchanging prefixes over eBGP peers, the administrative distance, the default administrative distance of eBGP peers prefixes is 20. So which means if I'm also learning those prefixes via OSPF, the eBGP route or prefixes or administrative distance is going to win over the default administrative distance of 110 of OSPF. But what if you really wanted your router to prefer the OSPF path? It was actually the more direct path, the shorter path, or the link that has the most bandwidth. In that case, you can go ahead and apply the backdoor statement to those prefixes, and that'll up the administrative distance to 200 on the eBGP learned routes, leaving your router to prefer the lowest administrative distance, in this example, which would be OSPF. So what I thought was interesting here was yesterday, what I was noticing was my external BGP routes, my external OSPF routes. Remember, the 1.1.1.1 is an external OSPF route. When I applied the backdoor statement to that, it stopped being advertised. So let's do that now. So we'll get into our BGP configuration, and we'll do network 1.1.1.1. We'll do a 32-bit mask, and we'll do backdoor. Okay, now if I come over here to BGP, hang on, it's there. I'm just going to do a hard clear. And give that a moment. All right, the adjacency is up. And again, on our middle router, which is the one we're redistributing from OSPF into BGP, we've now lost that prefix. It's not there. And if we go over to our end of the line router, show IP BGP, it's not seeing that prefix either. And so yesterday, I thought this was very strange, and I was sort of pigeonholing myself. And I was convinced that there was either a bug or that BGP just would not redistribute external OSPF routes when you apply the BGP backdoor or the backdoor network statement. So I kind of invalidated that hypothesis by going ahead and getting under the BGP configuration and applying a network statement to all of them with the backdoor. So remember 2.2.2.2 and 3.3.3.3 are both internal. So here I'll do clear IP BGP star. We'll let that adjacency bounce. It'll just clear out all of the routes on both ends since we just have the two neighbors. All right, neighbor up. So now if we do show IP BGP, now I don't have any of them. And if I don't have them in my local table, and I think I should have the 10 address in here, which is the local internal route. And that's not coming up yet. Right, we still have our routes in our routing table because we're still learning them via OSPF from the upstream router. But they're not in my BGP table, which means they're definitely not going to be advertised downstream. Yeah, and there's the one prefix we did not apply the network statement to. So I sort of debunked that yesterday. So when you're labbing things all night long and it approaches midnight and you just start to get tired, sometimes you just need to walk away, and that's kind of where I was at last night. So I'm glad I came back today and labbed this up to see backdoor in action. So we're not really seeing backdoor in action. What we're seeing is sort of a byproduct of what backdoor is actually doing. And it wasn't until I found this statement, which I thought I had prepared, here on one of Cisco's documentation websites, usage guidelines. This is for the network backdoor. To specify a backdoor route to a BGP learn prefix that provides better information about the network, use the network backdoor command in address family or router configuration mode. To remove the address, use the no form. Here's the syntax. Again, it's just simple adding backdoor to the end of your network statement. But here's the key point that I did not read yesterday, and I'm so happy I found it today. A backdoor network is assigned an administrative distance of 200, which we knew from yesterday. The objective is to make the IGP learned routes preferred. A backdoor network is treated as a local network, except that it is not advertised. And so that answers my question from yesterday. That solves the problem from yesterday. When you apply the backdoor statement to a network, it is no longer advertised via BGP, which, if I try to think about this in sort of a design aspect, you would not want to apply the backdoor statement to a network on a router that needs to be a transient router, right? A transit router, something that needs to take a BGP prefix from one interface or from one neighbor and pass it to another. You should not use the backdoor statement because it won't advertise to the other neighbor. And that's exactly what the documentation is telling us. I thought it was happening yesterday because of a bug. Turns out that's exactly how it's intended. Okay, so you're probably asking yourself, if you're not familiar with backdoor, why the hell do we have it to begin with? What's the purpose of it? So I'm going to open up the whiteboard and sort of show you what I did with the other routers 1, 2, and 3, where I set up the backdoor with the exact same topology. So all I did was I took, for routers 1, 2, and 3, I just took this router, which was all the way at the end, and moved it up here and just made a triangle out of it. So I'll go ahead and clear this. So again, I just have one router here and another router. This is 1, 2, and 3. They are all directly connected. And this is 10.1.12.0, 24. This is the .1, the .2. This is 10.1.23.0/24. This is the .2. This is the .3. This is 10.1.13.0/24. This is the .1. That's the .3. Here, let's see if I can do another color. Here we're running OSPF area 0, and I did it this way to show that I was including loopback 2 and loopback 3. However, I was not including loopback 1. Again, that is redistributed into OSPF. And routers 2 and 3 are eBGP neighbors. So if we take a look at this diagram alone, just the design of this network, what we should be envisioning is that these loopbacks are going to be advertised to router 3 and to router 2. We're going to redistribute them into BGP, and they're going to advertise them to each other. Now, because these guys are eBGP speakers, and eBGP routes learned from eBGP neighbors have an administrative distance of 20, in order for router 2 to reach these loopbacks, it's actually going to go to router 3 and then over to router 1, because it thinks that the routes learned from router 3 with the administrative distance of 20 is better than going through the directly connected link over to router 1. And to prove this, we'll just open up the lab, which I have router 2, put that on the bottom, router 3, I'll put that on top. So here we are on router 3 and router 2, and you see we have the exact same routing table. If I do show IP OSPF neighbor, you see we have the same upstream neighbor, which is router 1, and we are directly connected. Show IP BGP summary. We are directly connected and have a BGP adjacency already up. Now, if we check the BGP stanza, show running section BGP, I have the backdoor statement in here for these network. So actually I want to take them out. And do clear IP BGP star. That'll bounce the session, and then we'll see them toss their prefixes back over to each other. I should point out on each router, show run section BGP. I am performing the redistribution from OSPF, and it should be the same command, show run section router BGP. The same redistribution. And earlier I have no other configs in here. So now on router 2, show IP BGP. Good, we're learning our prefixes. And if I do show IP route, okay, so on router 2, we should be learning these prefixes show IP BGP from router 3, and we're selecting ourselves as the best path because they are because we're redistributing into BGP, so they're sort of locally originated. I guess the question mark means they've been redistributed in, but they have a higher weight value because we're generating them on our router. So if I shut down my interface facing router 1, I should use the backup routes from router 3. So let's do that. So that's interface ETH 00 shut. That'll drop our OSPF session. And show IP route, and we bounced right over to the BGP routes. And you see the BGP routes all have an administrative distance of 20. Now, I think if I no-shut this, I would think we're going to keep the BGP routes. Interface ETH 00, no-shut. Let's see if OSPF comes back up. So I'm doing I'm showing the routing table, and I'm waiting to see if the OSPF routes are going to take over. I don't think they should. I believe the eBGP routes with the administrative distance of 20 is going to beat out the OSPF routes. So if we do show IP BGP, just wanted to take a look. Looks like we only have a single entry from our BGP peer. But we should be seeing them from our OSPF neighbor. Okay. So I want to introduce the backdoor statement at the end of the network. So BGP 65,000. Let's do a network statement of 1.1.1.1 and a 32-bit mask. And let's do a backdoor. And we'll just do it all around the board. Okay, so the backdoor statement, show IP BGP. The backdoor statement Now we see we have a rib failure in our BGP table, which generally means that there's a better route in the routing table. And there is a better route in the routing table, which is the OSPF routes. And OSPF has administrative distance of 110. And when we do the backdoor statement, it ups the administrative distance to 200. So when I try to shut down that interface now, ETH00 shut. As soon as those routes, those OSPF routes are withdrawn from the routing table, the BGP routes should step in, and you see they have the administrative distance of 200. Even though I'm learning these prefixes via an eBGP speaker, an eBGP peer, so these should be administrative distance of 20 by default. But because we had the backdoor statement specifically, it is going to be administrative distance 200. So now if we no shut and that adjacency comes back up, loading to full, show IP route, the OSPF routes are back in with a better administrative distance of 110. So that sort of wraps up the lab. That was it was really good to be able to lab this up. I'm telling you, there's no better hands-on experience if you're not doing this every day in the field than labbing every night or every morning or any time that you have time to do it. Labbing definitely counts as experience. You know, when people, if any of you are struggling to get into IT or trying to get a networking job and you have your CCNA or something, or maybe you don't have professional experience, if you show someone that you've put in a few hundred hours of labbing and you can talk educated about protocols and operations, that's going to count as experience. All right, if you can, it's always just a matter of proving yourself. If you can prove yourself, you know, how do you prove yourself without on-the-job experience? You do it by doing labs. You do it by being the guy who stays up all night doing labs every night so you can get ahead, so you can be ahead of the next person. And that's why we do this, and we learn so much along the way. This was a great little lab, just one little thing, BGP Backdoor Network Statement. I wasn't sure exactly how it operated. I think I understand it pretty well, and I'm very glad I found that little bit in the documentation to say that it is not advertised. That was very helpful for me to understand. So again, I don't think using this statement would make a lot of sense on a BGP transit router, one that is passing prefixes from one neighbor to another, because you couldn't advertise that prefix, whatever you use the backdoor on. But I guess it has its place. I definitely see the value in it. I understand how it can be used, and I think it was pretty cool. So I hope it was fun to watch. And I guess that marks my time for the night. Tomorrow night, I think I'm going to dive into multicast a little bit. Again, I want to get back to my lab that I did on Sunday. I already graded it and reviewed it. There were two sections that threw me for a loop that I actually skipped and took complete zeros on, and that was QoS and multicast. So I definitely want to be prepared for this. And I did some reading on the lab pack that I'm using, and turns out they do get a lot harder as the labs increase, and that this first one was pretty easy. And with that in mind, it is actually rather disappointing, my score. I can't believe I actually scored so low on it. I don't know what to say. I can definitely see how some people sort of beat themselves up when they sit for the CCIE lab and they just have an off day. You know what I mean? You know, when you're just sitting there, you're doing your labs or you're at work or something, and you just can't find a good groove, you can't find a good rhythm, something throws you off, and and you're just sort of having an off day, you just can't seem to get the simple things right, I can definitely see how some folks, and probably myself, sitting for the CCIE lab could just have an off day, could just have a day where it's just not going right. And I think you need to have a combination of things need to happen, I think, for a successful CCIE lab experience. You know, you need to be fully prepared. You need to be well studied, well experienced, even if that's just doing labs. And you need to have a good day. You know what I mean? You need to. There's a spider crawling on my desk right now, right next to me. Now he a dead spider. You got to let things just roll off your back like a spider on your desk in a CCIE lab. You just got to see it, kill it, and move on, and not worry about it, not have it throw you off. You can't beat yourself up, I don't think, during the lab would not be a good idea, and that is definitely something I need to work on personally. I've definitely been hard on myself doing some of these large labs, both from I&E and from Cisco, and sometimes you just you trip yourself up, and then for me, my emotions take over, and I start to get furious. And that's definitely not a winning strategy. So I got some time to work on it. Let's all work on it together. Here's to success, everyone. See ya.